Everyone, welcome to this video on Bohr's model, which is lesson 4 in atomic structure and the periodic table. And this is where we finish our journey through the history of the atom. And again, like in quite a few of these lessons, I think what I'm going to talk about in this video goes a little bit beyond the spec. And I think it's well worth covering because this lesson in particular is the perfect introduction to quantum physics, and that's an area where a lot of teachers might not feel that comfortable talking to Year 9 students about quantum physics. But I think if we're going to give students this excitement about science and this idea that there are still questions that scientists are trying to answer, because fundamentally that's what science is all about. It's about raising and then answering questions. If we don't give them that sense, and if we never even talk about the science of the 20th century and quantum physics and so on, we're kind of cheating them out of the richness of what really makes science exciting. So this is going to be a little bit of a tough lesson, perhaps to teach, but a worthwhile one. I'm going to talk about how Bohr came up with his solar system model, and it's going to be a very brief sketch. There may well be some errors in here or simplifications, but I'll do my best to stay true to what actually happened. So we're going to continue, and you may be glad to know this is the last lesson for a little while, where we're going to talk about guess, deduce, and check. But we're going to continue with that model. And we're just going to remind students at the beginning of where we'd got to at the end of the last lesson, which was Rutherford's picture of this very dense, very small, positively charged ball of matter. Not a ball, sorry, I'm confusing myself with the plum pudding model. But the very dense nucleus in the center of the atom, which is, small and has a positive charge. And then, these electrons kind of scattered around outside. Now, if that model was true, then this could help us understand what's going on when we make observations from outer space. So what I would sketch here to students is a star like the sun. And I'm going to have a really simple model of a star here, super simple, that at the center of the star you've got this very hot core, and then around it you've just got, I'm going to put hot gases like this, hot gases like that. So this is a really simple model for the star, and what we're going to say is this star, and the sun is an obvious example here, this star emits light, but it doesn't just emit kind of one frequency of light. It emits light of all different frequencies. So I'm going to draw lots of different frequencies, and this will be going back a bit for them, but really it's not too important that they understand this in detail, as long as they've got a bit of a sense of where this idea was coming from. So we can draw some really low frequency light like that as well, and maybe a kind of intermediate one here. So you can draw all sorts of different frequencies like that. So the core is emitting light of all different frequencies. Now, if this was true, well, what happens with this gas here? Well, nothing much. Okay, what you would expect to happen is that all of the light that gets emitted by the core would end up at the Earth, and you may want to show them real pictures of what are they called? I was going to call them line spectra, absorption spectra. So these are those very pretty kind of colourful diagrams with black lines in. But what you'd expect is, if this was kind of amount of light, I'll just put intensity. I'll put an I for intensity, and this is the frequency here. I'm glossing over this, like I said. What you'd expect is that all frequencies would have roughly a similar intensity. You'd get light of all different frequencies. There wouldn't be any frequencies that you don't get. And that might be for an observer who's over here on Earth, detecting what light is coming from this star. So is that what actually happens? Well, not quite. So we're going to redraw our star here, these hot gases around the core, and I'm going to show again how you've got light of all different frequencies being emitted. Couple here, like that. All different frequencies being emitted. But what is actually detected on the Earth is not that you get all of the frequencies, and this was found in kind of the late 1800s, around that time. What was found there, actually, some of these don't make it. So I'm just going to pick a couple at random and I'm going to draw a cross to say some of them don't make it. Now, what does this look like in terms of our data? Well, if you were to sketch a graph of this, what you see, and again, this would be better if you show them actual real pictures, but I think it's helpful to relate the very abstract graph to what's going on here. So if I sketch this out, sorry, I'll do that in pen, intensity versus frequency again. What you get is most frequencies you get quite a bit of, but then weirdly, there's these frequencies where you basically don't get any light of that frequency or of that wavelength. So this is really surprising. Why is that? Now, what we want to illustrate to students is that this simple model that Rutherford came up with, this could not possibly explain what we've got here. Now, at the time, they didn't really seem to be related. This was known about long before Rutherford came up with this. No one saw that there might be a link between the structure of matter at this very, very tiny level and the light that you're getting from stars millions of light years away. And this is the genius of Bohr, is that he realized that the fact that this happens means that this guess cannot be true, because if this guess was true, you would expect all of the light to make it. The atoms in the gas around here wouldn't interact with the light at all. But Bohr realized, and there were others as well, Einstein has a big role to play in this, of course, but he realized that the guess must be wrong because this is what's observed. So we're going to need a new guess. If I zoom out again here and just bring it down here like this. So this is where we get to Bohr's guess. And he said, well, and I've forgotten a really important part. The really important part is where you got these little gaps, the very specific frequencies of light that didn't make it to Earth, where you got those little gaps depended on the element. So if you had a star where most of the gases around it were hydrogen, you would have, let's say, this frequency and this frequency. But if you had a star where most of the gas around the core was helium, for example, they might be here and here. So you might get other parts. And again, show them pictures, show them line or absorption spectra to show that for hydrogen, you get two black lines here, let's say. For helium, you get them here, whatever that might look like. And what Bohr realized is that different atoms must have different structures. And he imagined it, and maybe he was thinking of out in space because of these spectra, but he imagined the atom to be like a tiny little solar system. So he sort of said, well, it's almost as if these atoms are like tiny little solar systems, where you've got your nucleus in the middle with this positive charge, as Rutherford had said. But it's almost like the electrons can only be on very specific orbits around the outside. So I'm going to just sketch an electron here. And what Bohr realized, and this is, I think, where it gets really, really mind-blowing, clearly a very clever guy, what he realized was that the reason that certain frequencies of light were not making it through to Earth was that it was something to do with the distance between two possible orbits. So he said, well, you might have electrons on this orbit, you might have electrons on this orbit, but it's to do with electrons jumping across a specific, we can call it a specific distance, really it's a specific energy, but jumping across a specific energy gap or distance that causes this light to be blocked. And this was how he explained, let's say this is hydrogen here, well he said, well maybe helium has got a different, it looks like a different solar system. So maybe we could put the electrons closer here, although that wouldn't really be the case, but anyway, doesn't really matter. And then this one here. So he said helium maybe has a different structure, the electrons are at different distances away from the nucleus, and therefore that gap is different, and that's why you get different frequencies being absorbed. So this is the solar system model. Now, you don't need to go into loads and loads and loads of detail about this. It's you know, what do students need to know? They need to know that Bohr said there were shells, basically, and energy levels would be a better way of describing it, but we can call it shells for the time being. Bohr said there were shells. That's fine. But I think it's worth talking about this because what you're seeing here, A, links to what's happening in physics, certainly triple physics, towards the end of year 11 in the waves topic when they learn about kind of black body radiation and emission absorption of electrons, of photons because of electrons jumping between shells. They learn about all this stuff in physics, so I think it's quite helpful to introduce this very basic principle. But it's also a way into talking about some of the big mysteries, because this was super controversial. Not everyone believed this. You're saying that the electrons can only be at certain distances from the nucleus. Well, who says? Why is that? Why would it be that they can't be, you know, they can't be here and they can't be here? And this was an argument that went on, and actually these ideas nearly failed in the early 1920s. A lot of people were willing to write off Bohr's ideas as a load of nonsense, and it was only when Heisenberg and later Schrödinger came up with wave mechanics that they found a way of explaining all of this and how it all fit together. And you can get on some really cool stuff then. You can introduce the uncertainty principle and some of the cool bits about quantum mechanics. And I think, I mean, this is just my view. Your head teacher may disagree, but I think it's fine. Show some videos here and you know, get on some more philosophical discussions, because really that's what science is all about. So this lesson, in terms of the substantive kind of facts that you want them to take away, is quite limited. But I think it opens up lots of possibilities for a really rich debate about science, the nature of science, and of course the history of science, that hopefully your students will find inspiring. So that's how Bohr came up with his solar system model. This, of course, is the model that students are going to use for the rest of their time in GCSE science. So in the next video, we'll look at how to introduce this model in a more kind of structured way, and get them thinking about the kinds of notation we use when thinking about atoms.